Very good morning, good afternoon, good evening, my dear friends. I always give you an introduction so it becomes much more lively for the discussions. So, I am Raghunandan Sengupta from the IME department, IIT Kanpur, and I am the instructor for this NPTEL course, which is Total Quality Management 1. And as you know, I did mention time and again when I started the course in between also, the main Bible based on which we are trying to study this course is the Montgomery book, which is absolutely fantastic, and all the references, everything is basically taken from them. So, if you have a little bit of quantitative background, you are interested in trying to study statistics from the quality control perspective, that is an absolutely fantastic, fabulous book. So, we are, as I said, we are interacting based on TQM1 course, which is Total Quality Management 1 course, and this is the 22nd lecture, which means we are in the 5th week. And if you remember in the 21st lecture, the fag end, I did discuss about the limits based on the central values, which is x bar bar and some plus minus values, as well as r bar and some plus minus values. And the last slide on the 21st lecture, I did mention that how the depending on the sample size, the coefficients can be decided, and we can use those coefficients for our further calculations. So, continuing the discussions, the reference charts, again you have the observations in samples which are given. The factors for the central lines D2 and reciprocal of D2 are given, and chart for the ranges depending on the suffixes for D, whether small or capital, are given, so that you can understand that depending on the sample observations in the samples, which is n in size, you can basically calculate and use those values for your corresponding calculation. Now, unbiased estimator of sigma is very important to know, that in the sense that if your calculations basically gives you some value from the sample which is not able to predict the actual population parameter best, even if the calculation seems very fine, so obviously there is some problem. So, they should be unbiased in the sense the difference or the technical difference between the population characteristics and the sample characteristics should be as close as possible to 0, the differences. So, if R bar is the average range of m samples, so you have, if you remember, you take one sample which is of size n, you take the second sample which is of size n, and you continue doing this. So, if R bar is the average range of m samples, then to estimate the sigma, we use the formulas accordingly, and which is the unbiased estimator of sigma is given by the, and okay, by the way, let me also mention that in clear terms. So, this value of sigma hat which you see, so this is like, which basically is an estimate. So, that is basically coming from the sample, and the actual population 1 is basically given by standard deviation, which is sigma. So, what you do is that use this sigma hat in order to predict sigma. So, there is an unbiased estimate of sigma is given by the ratios of the range divided by the average range divided by D2. So, D2 would basically depend on the sample size. So, depending on the sample size, you can find out D2, use that to find out sigma hat. So, that will give you a best estimate for the population parameter sigma. Now, we will consider the phase 1 of the overall process of the control charts. Since at the beginning the charts uses preliminary samples, the control limits are treated as trial control limits, which will be finalized later on. To check if process was in control during the initial m samples, plot the charts and look for any pattern or any points which are outside the control limit. So, technically, that if there is no variability, but there has to be some stabilization on the process, you will continue taking the observations plotted. So, once the variations technically become stable, you will be able to basically proceed with the calculations. To check if process was in control during the initial m samples, plot the charts and look for any pattern or any point outside the control chart. So, if there are, obviously there should be such warnings which you should take care in order to basically find out the estimation process is best without any error. If there are points outside the control limits, revise the control limits and do your calculations accordingly. Check assignable causes for each of the points outside the central limit or the control limits. If there exists an assignable cause, discard the point and recalculate the control limits with the remaining points and continue doing it likewise. So, if there are some assignable causes which you know should not be taken, you basically take that set of observations out. Phase 1 of the control charts continuing. If no assignable causes, if they are found, discard the point without much justification, retain the point and see if in future if process remains in control, and then you take decisions accordingly. If initially a lot of points remain out of control, then it means that you should dropping too many would reduce the availability of the data points. So, if you basically drop many of them, the sample size will really decreases, which gives you a problem, because for a small sample size, trying to predict for the population parameter becomes, or population characteristics becomes difficult. So, inspecting causes for all the points may not be possible or worthwhile, because that will entail money. So, in such cases, look for patterns in the control charts, take the decisions accordingly. Identification and removal of process problem causes major process improvement. So, if their problems are eliminated at one go, you are able to improve the process capability, and the improvement of the whole process problem takes place. So, let us consider an example, a hard break process. So, this is basically taking from a section 5.3.1 from Montgomery book. A hard bake process is used in conjunction with photolithographic in semiconductor manufacturing. We wish to establish statistical control of flow width of the process, such that it resists in the processing using X bar and R charts. 25 samples are taken. So, this information is given in the table. For the first column, you have the sample number. So, 1, 2 till 25. Each, now you will be asking what is the number of observations which is there in each sample. So, that is given as 5. So, if you read it where I am hovering my pen, it says that 25 samples, each of size 5 is taken. So, n is 5, m is 25. Has been taken when we think of the process is in control. The interval of time between samples or subgroups is 1 hour. So, if you remember, I mentioned 9 o'clock, 10 o'clock, 11 o'clock, so on and so forth. So, the time difference between the set of observations you are doing is basically given as in 1 hour. The flow width measurement data in microns for these samples are shown in figure 16.1. So, I am again mentioning, along the first column you have the sample number, each sample is of size 5, and the wafers basic informations are given. So, the cell 1 which I am marking now, where I am putting my pointer, is basically the reading for the first sample, the first observation. Similarly, if I check up the first sample, the fifth observation is given by 1.6914. So, based on that, what I do is that I find out the sample averages. So, this 1 point where again my highlighter is pointing, I am not trying to draw it. This 1.5119 is basically the sum of all these things divided by 5, which is the average of that particular sample. And the ranges, which is given as 0.3679, is basically the difference between the maximum and the minimum. So, we basically find out those values for the second sample, third sample till the 25th one. Similarly, we do and try to find out the ranges for the second set of observation, third set of observations till the last one. And if you see at the fag end of this table, what the problem does is basically gives us the X double bar, which is the average of the average. So, what we need to do is that the first observation which is given here is 1.5119 is X1 bar, which is 1 means the first set of observations of 5 and the bar means the average of that. Similarly, if I consider 1.5805, that would give me the average of the seventh set of observations, where the set of observations are 5. Similarly, I have the ranges which I have already mentioned. So, X bar basically means sum of all these things divided by 25, which comes out to be 1. Let me highlight it, it will be easier. So, this is basically the average of the average, and this is R bar, for the average of the range. So, now the central line would be given by the, for the average would be given, for the range would be given by the sum of them divided by 25, which comes out to be 0.32521, and the control limits for the chart depending on the values of the coefficients which are already discussed in the table, which we did few minutes back, would give you the lower control limit at 0, the upper control limit as 0.68749, which I now draw it on the table. So, what we are doing is that we are trying to basically plot the observations set number along the x axis. So, the first one where I am highlighting is the first sample of 5 observations. If I mark this where I am now hovering my pen, it is basically the last observation for the 5 set of observations which I have. So, all these dots which are there are basically the sample average. The central line which is there, sample average means for with respect to the range. The central line which is there, which I will try to highlight using the red color. So, this is basically R bar, which is as given as 0.3252. So, from where does it come? We have already calculated accordingly. So, LCL, which is the lower control limit, is 0, which is marked here. The upper control limit is 0.68749, which is given here. So, you can find out that how the overall fluctuation of the range values occurs within this limits of upper control and lower control with a central line. Now, if I go to the x bar charts, I do the same calculations. I find out x double bar, which is the sum. If you remember, the second last column were all the averages, x1 bar, x2 bar, x3 bar till the last one. So, I find out the averages, which comes out to be, again I am using the red color highlighter, is 1.5056, which is this line, and the upper control limit and the lower control limit are given by the formulas as given here and here. So, this x bar double bar is coming from 1.5056, this R bars you have already calculated, and this A2, which is plus minus, will depend on the sample size, which you find out from the table. So, these values, upper control comes out to be 1.6932, which is plotted here, and another value is 1.31795, which is plotted here, and then you see the plots have been made. So, the plot where I am hovering now my pen is basically the average of the first sample. If I consider this, which is the last one, would be the basically be the as average sample average for the last set of observations of 5 taken together, which is the 25th one. Now, you want to basically find out estimating the process capability. Estimating process case standard deviation basically can be found out from the formulas, which is the best estimate, which is sigma hat is equal to R bar divided by D2, and that comes out to be 0.1398, which is about 0.14 micron. Estimate of the fraction of the non-conforming wafers produced is found out. So, you want to find out what is the control limit or the dispersion or the probabilities. So, assumptions are flow width is normally distributed, which is a major observation observations and comment based on central limit theorem. You find out the means, which is 1.5056, and the standard deviation you have already found out is 1.39. You use that concept of mu minus z alpha by 2 into whatever the coefficient should be, depending on 1 sigma, 2 sigma, 3 sigma, and the other values would be plus of that, because you are going on the right hand side. So, you want to find out the probabilities. Those probabilities are very simple. In this, the first formula gives you the probability that the x values are less than 100, and the second value gives you the probability of the x are greater than 100. So, you use the standard normal deviate and find out those values. So, standard normal deviate formulas, I will just write it down. So, this will be probability of x less than 100. So, this will be probability of x minus mu by sigma less than equal to 100 minus mu by sigma. So, these are what I am doing is I am converting from the standard normal to the standard normal deviate. Using that, if I have, so in this case Let me use an eraser so it is easier for me to note. I use a highlighter of color blue. So this formula is this, and which means once you use the standard normal deviate, and the color scheme for this would give you. So once you have this, you find out the values for the standard normal deviate table. The values comes out to be about 0.35 into 10 to the power minus 5, which means that about 0.035 percentage or 350 parts per million ppm of the wafers produced will be outside the specifications. Now you want to find out the estimating the process capability ratios. So process capability ratio is expressed as the difference between the upper control and the lower control divided by 6 sigma. 6 sigma is coming from the total width. So if it is plus 3 sigma onto the from your side, plus 3 sigma onto the right and plus sigma onto the left. So for my case it will be left and right. So it's just the reverse. So if I am basically putting about 99.97 of the total coverage is between this plus minus 3 sigma. So obviously I will divide by 6 sigma. If I am trying to basically find out to a coverage probability of about 95, then obviously it will be plus minus 2 sigma, and if it is basically a coverage of about 67, it will be plus minus 1 sigma. So that's why the 6 value which is there in the denominator signifies what is the level of such coverages which you are covering. So basically it means the upper control minus the lower control, which is the differences which you have. So if I check the, so this is the upper control, this is the central line, this is the lower control. So these is the differences which we have. For the other example, if you want to find the process capability, you find out the differences of the upper line and the lower line and divide by 6 of the sigma, which is the standard deviation, which I have already found out as 0.13698, and it comes out to be 1.192. Another way to interpret the process capability would be that process capability will be given by 1 by Cp, and the percentage of the specification band that the process uses can be utilized accordingly. So for the above example, the concept of process capability gives us the value of about 83.89 value. So just trying to recap, practitioners established regular periods for review and revision of control central charts, such as every week, every month, every day, or whatever the frequency is. Highly desirable, it's basically highly desirable to use at least 25 samples, because each sample set may have 5, 10, 15, whatever, but the larger the total set of observations are throughout the samples, which basically would mean that you have been able to find out the characteristics of the sample based on a larger sample, such that it will mimic the population to a much greater extent. So if you remember, biasness and all these things should technically decrease. Sometimes the user will replace the central line of X bar charts with the target value. So it is helpful in shifting the process average to the desired values and make calculations accordingly. Processes where mean may be changed by a fairly simple adjustment of a variable that can be manipulated in the process can be utilized, but it will obviously have some justification why you are trying to do that. Once a set of reliable control limits is established, we use the control chart for monitoring the future production, which is basically the phase 2 of the utilization of the chart. So first you use phase 1 concept of drawing the charts and bring a control, and then use this control to go to the second stage to find out whether the process capability is changing or is fixed. Some guidelines for creating the charts or X bar and R chart size rationale for the subgroup should be done, such that X bar charts monitors between sample variability in the process over time. The R charts or as done here would basically measures within sample variability. So what you are doing is that within the sample variability you are trying to measure by finding out the difference between the maximum and the minimum. So it basically means that the averages which you are trying to use from the X bar basically means for the sample averages throughout the sample, and the R, obviously R bar would come later, but the R which you are trying to use would be the variability for each sample. Then you average it out for the whole set of m number of samples, which would technically be equal to, in the respect that the information which I am getting from such samples which are being combined together should give us the maximum amount of information about the population. So, rational subgroups concept means that subgroups or samples should be selected, so that if assignable causes are present, the chance for differences between subgroups would be maximized, while the chances for difference between those to be assignable causes within a subgroup would be minimized. So, obviously, you do your calculations accordingly. Some guidelines, as I was saying, to design the X bar and R charts, we must specify the sample size, control limits, widths, and the frequency of the sample to be done. So, whether it is weekly, monthly, hourly, based on seconds, that will basically be decided beforehand. We will also decide on the number of observations which are there in each sample, and we will also consider the number of samples. It has been mentioned it should be 25 or more. We will try to basically understand that also and keep that in mind. If the X bar chart is used to detect moderate to large processes, shifts of 2 sigma or more, then the smaller sample size is effective, because in that case what you are trying to do is that you are trying to basically find out small sample size and technically take more of them in order to basically elevate your, or basically overcome the problem of trying to take all the set of observations at one go. For detecting small shifts, sample size can be about in the range of 15 to 25. So, obviously, we will have the m size also depending on that, which can be made such that the overall number of observations which you have, which is n into m, would give you a good idea that about the characteristics which you find for this whole set of observation, which is n into m, would in the long run mimic the population parameter or the characteristics to the maximum possible extent. The R chart is relatively insensitive to shifts in the process standard deviation for small samples. Sample of size n, which is 5, have only about 40% chance of detecting on the first sample a shift in the process standard deviation from S2 to S. So, there are 60 of them would give, 40 would not give you that information. Consequently, for large n, say n greater than 10 or 12, it is probably best to use a control charts for S or 2S instead of R accordingly. So, the problem of choosing the sample size and the frequency of the sampling is done one of the allocating the sample effort, based on which you can increase your efficiency for the sampling. So, let us consider an example. A tungsten wafer layer is deposited on the substrata using a sputtering machine, which is given, and the data related to that is given in table 6E13, which consists of layer thickness measurements in angstrom and 20 subgroups of 4 substrates. So 20 which you have is basically the first substrate is 1 to 4, second one is 6 to 8, and so on and so forth. So what you do is that you need to find out and set the X bar charts and the R control charts on this process. Now, you want to answer, is this process in control? If not, what are the problems? So, obviously, you have to take some decisions accordingly. Revise the control limits and do your calculations again. Estimate the mean and the standard deviation of the process such that you will try to find out the sample mean which you find out, the sample standard deviation you find out, whether it mimics the population parameter to the maximum possible extent. Is the layer thickness normally distributed? That is the question we need to answer. And the last question we need to answer is that specifications, if they are at 450 plus minus 30 values, then estimate the process capability and comment intelligently. So, what we do is that we write a R code. So, the data is basically stored in matrix with n rows, which is 20, and n columns is 6 as already mentioned in the part of R, as well as if you have seen the data set which is given here. So, the values are all given. So, if you want to basically find out the first column and all the values of the rows, you will give this function as data comma 1, and it will give you all those values accordingly. So, you basically recall those library functions and try to basically fit the functions as X bar and R, and you do your calculations accordingly. So, once you run the code, the distribution, so not the distribution, the process capability chart would look like as given here. So, here the groups are there. So, and you find out the number of groups is 25, and you find out that there are 4 of them each. The central values, the standard deviations are given here. I am not going to the calculations, you can find it out. The upper control limit and the lower control limits are given. So, based on that, if I study, the graph is always between the upper control limit where I am basically marking and the lower control limit which I am marking. But obviously, there is one outlier. So, if there is an outlier, you have to basically think that how actions can be taken accordingly. So, what you do is that eliminate some of the observations, redo the calculations. Once you redo the calculations, the graph which gives you the information which is in front of me shows that the outliers have been removed. So, this can be done very easily in Excel sheet, in R, programming, whatever it is. So, continuing with the example, as can be seen from X bar charts, the last point is out of control, which is the red one. We remove the point to recalculate the control limits on both the cases, and in real life we can do this only after finding some SNML causes. Arbitrarily you cannot remove it. Obviously, there is some reason why it has happened, and we want to understand that. So, once you do this, all using the art packages and the values which are given for the readings, you can very easily draw this graph, do some statistical analysis in order to basically find out whether they are ascendable causes or non-ascendable causes based on which the outliers has happened. So, mean can be seen from the charts. We will estimate the standard deviation of the after 2 slides. So, continuing with the example, to check normality, we draw the QQ plots, which is quantile plots, which anybody can check in from a very good book. A QQ plot is a scatter plot created by plotting 2 sets of quantiles against one another. If both sets of quantiles came from the same distribution, we should see the points forming a line which is the roughly a straight line and 45 degrees both to the x axis and the y axis. If checking normality, one quartile is taken from the normal to see if the data set is also normal, we can do that, and you can basically check the normality test also and basically comment accordingly. So, now I have plotted the QQ plots. So, this is the 45 degrees line which I was talking about. So, along the x axis you have the theoretical quantiles, and along the y axis you have the sample quantiles. So, you will see that they are almost the same, only the outliers is happening here. Technically, obviously, if you go into depth, you can find out more outliers and comment intelligently, but the outliers are happening on the values which are very high. So, continuing the example, checking process capability gives you the first we estimate the standard deviation given by R bar by D2, which comes out to be about 16.65 divided by 2.04. So, n is 4, you remember that. It comes out to be about 8.1. For this calculation, we use the values that include the 18th point also, because you remember if the outliers are removed depending on the ascendable and non-ascendable causes, you should basically be satisfied yourself that the step you are taking is right or wrong. Now, once you find out the process capability, it comes out to about 1.2376. I will discuss all these things in more detail with more different type of charts, and with this we will conclude this 22nd lecture and continue with the 23rd and more for the TQM class. Have a nice day. Thank you.